In this video, we use Abaqus to model a plate with a hole similar to the previous problem, but the difference between this video and the previous one is that the thickness of the plate here is 3 centimeter, so we cannot model this as a plane stress because the plate is thicker. We are going to create a 3D model for this problem, and similar to the previous video, we take advantage of the symmetry and model only this portion, 1/4 of the plate in our finite element model. So let's go to Abaqus. We create a part. The model is 3-dimensional, deformable, and we use solid, and we use extrusion as the type for this model, and continue. Similar to the previous video, I create the whole plate first, and the dimension of this part is 250 millimeter, and this one is this one is 100 millimeter. All right, and we create a hole at the center. The radius of the hole is 10 millimeter, and the hole should be right at the middle. So 125 millimeter from the top edge, and 50 millimeter from the left edge, and we click. We're done with this, and the thickness of the plate is 3 centimeters, so it's 30 millimeter. So this is the domain that we have, the entire plate. Now if I go back to the sketch, now I can basically trim the parts that I don't need. So auto trim here, 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 here. We don't need this, this, and this. So done. And we have to regenerate this. So we, after regenerating the features, then this is the model that we wanted to get, basically only 1/4 of the plate. Now after having the part, we can create the material properties. Steel, it's a steel material. The material is a steel. Elasticity modulus is 200 gigapascal. I'm using Newton for the unit of force and millimeter for the unit of length. So this is 203 megapascal, and Poisson's ratio is 0.3. We create a section. It's a solid, homogeneous, continuous steel, and this time it's not plane stress or plane strain. And we assign the section to the entire part. After this, we go to assembly and bring one instance of the part to the assembly. Then we define a step, and we created a static step. All the default values are good. We don't need to change outputs here. And we go to load. So let's create the boundary conditions again. So we apply rollers on the bottom face and the left face. So let's select this face, done, and we fix this in the U2 direction. So we prevent this from moving in the Y direction. And we do the same thing with the left edge. Again, roller, I call this one roller 2. Continue, we select this edge, this surface, and this time we prevent this surface from moving in the X direction. Okay, the last piece is to apply tractions or forces on the top. So create load, and pressure is good. We select this, we select the top surface, and the magnitude of the force is 25 megapascal. Because it's tensile, we put negative here. So we have defined all the loads and boundary conditions. The next step is to mesh it. Similar to the previous video, we want to have a finer mesh close to the hole, because we want to be able to capture the stress concentrations around the hole. So we're going to seed the edges. We have to mesh this on the part, because this is a dependent part. So we select this edge and this edge, done, and the number of elements is 20. I change this to 10, and I use single. Single for the bias. The directions of the arrows are wrong. We want to flip them. So let's select these and this and flip them. So basically the direction of the arrows show the direction of the refinement. And apply. So we can see we have finer mesh here compared to here. All right, let's do the same thing with the left surface or the left edges. We select these two edges here. This time the directions of the arrows are correct. I use more number of elements here, and still again I'm using bias, and done. And finally, let's define the number of seeds over the whole surface. I'm going to use a uniform mesh, no bias, and I use 15 elements here. And the last thing is to define the number of elements over the thickness of the plate. So let's select this edge and this edge, and we use 3 elements over the thickness. All right, so we need to define what kind of element shape we want. We can go with hexahedral, tetrahedral, or hex dominated. So I'm going to go with hexahedral this time. And okay, we need to make sure that the element type is correct. So it's 3D stress, linear is good. So okay, and we mesh the part. So this is the mesh that we have. It's finer close to the hole. In practice, you may want to have a finer mesh, but this is good enough for this tutorial. After that, we create a job, 3D plate, continue, okay, and let's submit the job. This shouldn't take too long, so hopefully after a couple of seconds we should have the results. So the model is running now, and the processor is completed. So now we have the results. The analysis is completed. Let's look at the results. Similar to before, we can look at the stresses, the Mises stress, or we can look at the six components of the stress, sigma 1 or stress in the x direction, stress in the y direction. You can see we have a stress concentration around the hole, or you can look at the shear stresses. They shouldn't be too big here, and or the principal stresses. If you want to, you can look at the deformations, or if you want, you can prepare reports for the support reactions, deformations, or stresses.